So in this example, we're asked to find alpha, the velocity correction vector, for a round pipe flow with a parabolic profile where the velocity at any point along the radius of the profile is equal to the maximum velocity times 1 minus r over r squared. Okay, so in this case we're given this setup, and that little r is like this, and that this distance here is capital R. Okay, and then we have a round pipe. And we're also told that it's a laminar flow. And again, we're just asked to find the velocity correction factor alpha. Okay, so what we know from this is that V bar is equal to 1 over A times the integral of V dA, and that alpha is equal to 1 over A integral over the area of V over V bar cubed dA. All right, so that we first need to solve for V bar so we can plug it into our equation for alpha, and then take that integral will give us our alpha term. Okay, so just like we did before, we need to think a little bit about how we're going to define our differential area so that we can set up the integral. And again, just like we've done for all the cases where we've had a round pipe, so we have some sort of round pipe like this, we're going to pick our differential area to be some radial slice like this, where we'll define this distance as dr, and this is dA, where dA is going to be equal to 2 pi r dr. Okay? So now we can set up our integral. So let's first solve for V bar. So we're going to say that V bar is equal to 1 over pi r squared times the integral from 0 to r of V max times 1 minus r over r squared times 2 pi r dr. Okay, that's just 1 over the area times the velocity times integral of area times velocity times the differential area. All right, so we can take that integral. It's pretty straightforward, and we get 2 over r squared V max times r squared over 2 minus r to the 4th over 4r squared, evaluated from 0 to r, and that's equal to 1/2 V max. There's V bar, so you get 1/2 V max. All right, and so now we can plug that into our equation for alpha. So we get alpha is equal to 1 over pi r squared times 1 over 1/2 V max cubed. So because that's not dependent on r, then we can pull that out of the integral, times the integral from 0 to r of V max cubed times 1 minus r over r cubed times 2 pi r dr. Okay? All right, so we could rearrange that pretty easily and get something that looks a little bit more easily managed. And that equals 16 over r squared times the integral of from 0 to r of 1 minus r over r squared cubed, forgot a square up here, times r dr. Okay, so that gives us an equation that we can solve to get alpha. It's not entirely straightforward. In fact, that integral is a little bit hairy, and so instead of going through the entire derivation, the entire integral, what I'm going to do is do a change of variables. So we're going to look at changing variables. So what we're going to do is say q is equal to 1 minus r over r squared. Means that dq is going to equal negative 2 r dr over capital R squared. So we're going to plug that in, and we're going to get alpha is equal to negative 8 integral from 1 to 0, and that just is because of how we define q. So at r equal to 0, q is equal to 1, and r equal to capital R, q is 0. So now we're going to integrate from 1 to 0 in our new variable q of q cubed dq. That's equal to 2 q to the 4th evaluated at 1 and 0. That equals negative 2 times 0 minus 1 equal to 2. So for laminar flow, in a round pipe, alpha equals 2, and it'll always equal 2. All right? So that's a pretty straightforward example of how we can use alpha. And now for any laminar flow and any round pipe problem that you ever do, you can just put in alpha equal to 2, and then you don't have to worry about the variations in the velocity field of that cross section. All right? So in the next video, we'll go over some more applied type examples.